Hi, thanks for tuning in. I'm Eduardo Fonseca from the Music Technology Group in Barcelona. In this video, I'm presenting our WASPA paper on self-supervised learning of audio representations. Our paper is titled Self-Supervised Learning from Automatically Separated Sound Scenes. This work was done during an internship at Google Research and in collaboration with multiple researchers at Google, as you can see in the slide. Our task is to learn audio representations from unlabeled data. To do this, we turn to self-supervised learning, where we learn representations without explicit human supervision. The success of these methods relies on the design of proxy tasks. By solving these tasks, we learn mappings from inputs to low-dimensional representations, which can then be used for downstream tasks. Specifically, our work focuses on contrastive learning, which is basically learning by comparing. So we compare pairs of positives and pairs of negative examples. The goal is to produce a semantically structured embedding space where representations for similar examples are pulled together and representations for dissimilar examples are further away. So the key factor here is how we design these proxy tasks, and there are two main questions. How to generate the pairs of positive examples, and once we have them, how to compare them in order to learn useful representations. One common way to generate pairs of positives is through data augmentation, in order to have differently augmented views of the same input example. For contrastive learning of audio representations, it is popular to employ compositions of augmentations, using methods like those in the slide. In most cases, these augmentations introduce artificial handcrafted transformations, each with one or more parameters that must be tuned. So when we combine many of these things together, we run the risk of introducing a somewhat unrealistic domain shift. On the other hand, sound scenes consist of time-varying collections of sound sources, each generating characteristic sound events. The association of these constituent sound events with a mixture and each other is not random but semantically constrained, in the sense that not all the classes coexist naturally. With this motivation, we explore the use of automatic sound separation to generate views for contrastive learning. In particular, we propose to decompose a sound scene, which in general is a mixture of multiple events, into multiple separated channels that share semantics with the mixture and with each other. Compared to previous approaches, sound separation is an input-dependent process that produces ecologically valid views, and it also reduces the need for parameter tuning once you have a separation model. Specifically, the comparison of the input mixture and one of the separated channels should be suitable for contrastive learning. On the one hand, the mutual information between views is reduced, as some sound components from the mixture are no longer in the separated channel. Also, some relevant semantic information is preserved, as the sounds present in the separated channel are also present in the input mixture. The second question is how to compare pairs of examples. There are two popular proxy tasks for contrastive audio representation learning. Similarity maximization, also known as SimClear, consists of maximizing the similarity between differently augmented views of the same example. Coincidence prediction consists of predicting whether a pair of examples occurs within a temporal proximity, typically a few seconds of an audio clip. Here, we propose to optimize both tasks jointly as a multitask objective. This can favor learning complementary information because both tasks share the same goal of a semantically structured embedding space, but each task pursues this goal in a slightly different way. Similarity maximization aims to collocate the representations of positives at the same spot in the embedding space, whereas coincidence prediction is based on a weaker condition, establishing a relationship between the representations but not necessarily requiring their collocation. And this is our proposed approach. It is composed of a front end that includes sound separation and augmentation to generate pairs of examples, and the backend with two proxy tasks, similarity maximization and coincidence prediction, each with a corresponding loss function. Here the input is audio waveforms, which are converted to MEL spectrograms, and the output is a low-dimensional representation H after the encoder. In the augmentation frontend, every incoming mixture is separated into two output channels, from which one is randomly selected for each task, and then the outcome goes through a data augmentation block. For sound separation, we use a model trained with mixture invariant training. Mixit is a method in which training examples are constructed by mixing audio clips, and the model is tasked to separate the resulting mixtures into a number of latent sources. This method is fully unsupervised, so it allows leveraging large amounts of unlabeled data, in our case, audio set. Also, it has shown promising results in universal sound separation. Our separation model is based on an improved time domain convolutional network, which is similar to a COM testnet. Now, it is typically beneficial to use a composition of several augmentations. In this way, we define a more challenging learning task, which leads to more effective representations. In our case, we combine sound separation with temporal proximity sampling and spec augment. Temporal proximity sampling consists of randomly selecting two audio snippets to construct pairs of examples, instead of using the entire audio set clips. We use snippets of 1 second. Then, spec augment includes time warping and time and frequency masking. So, in this way, we create our pairs of examples. Note that each data augmentation block is actually a different instance of the same augmentation policy. Also, the slide illustrates the creation of positive examples, where we compare a mixture with one of the separated channels. To create a pair of negative examples, we would compare different clips. And finally, our pairs of examples feed the two proxy tasks. For the similarity maximization task, we use an encoder to extract low-dimensional embeddings H, and then a similarity head to map to the embeddings that feed the contrastive loss. This loss maximizes the agreement between embeddings that correspond to differently augmented views of the initial audio example. For the coincidence prediction task, we use the same encoder to extract embeddings H, then we concatenate the pair of embeddings, and then a coincidence head is tasked to predict the probability that these two guys coincide within the same audio clip. This is a binary classification task, and so we use a binary cross-entropy loss. So we train all this until convergence, and once the training is over, the representation H is used for downstream tasks. As for implementation details, we separate input mixtures into two channels, as it was proving more practical than using a larger number. Our encoder is a CNN14 from the Pan paper, which has a VGG-style architecture, and we obtain our representation H after a bottleneck to 128 dimensions. Also, our two heads consist of a simple multi-layer perceptron with a real nonlinearity. For evaluation, we employ two methods. The first one consists of a downstream classification task with a shallow model. Specifically, we use the trained encoder as a feature extractor, and we compute features on audio set. Then we train and evaluate a shallow network on top of these features. In addition, we also evaluate the embeddings following a query by example retrieval task. But in this video, we focus only on the results for the shallow model classification. And here's the summary of the main results. First, we show the utility of sound separation for contrastive learning of audio representations. The table shows the performance obtained by creating pairs of examples in different ways, coupled with the similarity maximization backend. In particular, temporal proximity sampling is always applied, and sound separation and spec augment are applied as indicated in the column. So the first row corresponds to only temporal proximity sampling, and then in the second row we add only spec augment or only sound separation in the third row, and finally we combine everything. So we see that sound separation preprocessing outperforms spec augment, yet the best performance is obtained from their composition. This indicates that comparing the input mixture with the separated channels provides better representations than the conventional setting of using only the input clip. Also, results show that sound separation can be successfully combined with other commonly used augmentations. During our experiments, we saw that sound separation is beneficial, even when the separation is less than perfect. This can happen when the input mixtures are difficult to separate. So we wanted to see whether the processing provided by a separation model before convergence can also be a valid form of augmentation. To this end, we experiment with separation examples generated by multiple training checkpoints of a separation network. We view these separation checkpoints as audio processors, and we identify 4 types. The slide shows the spectrograms of the 2 separated channels obtained with 4 checkpoints of the same separation model. And this is for an input mixture that contains a guitar melody followed by the sound of applause. You can see the processor's name along with the number of training steps here at the top. So the processors include separation after convergence, S2, which is what we used for the results in the previous slide. Separation before convergence, S1, where the separation performance is more limited, as you can see in the slide. And then we also have a filtering effect, where sources are not really separated and the output channels are differently filtered versions of the input. And finally, a noise process, where outputs are produced by the separation model untrained, featuring clearly audible and wideband noise. From the results, we can make 2 observations. By looking at the top section of the table, we see that all processors provide valid forms of augmentation for generating positives. And by looking at the bottom section, we see that combining some of them using an OR rule can be helpful. This means applying only one of the processors selected randomly at a time. Finally, we show the results when training the entire framework, meaning jointly optimizing both proxy tasks. Here we observe small boosts across the board. So these results suggest that the key ingredient here is not the quality of the sound separation process, but rather the combination of diverse processing provided by the separation model as learning progresses. To put our results into context, we compare them with previous work, and we see that the proposed framework outperforms some past approaches, including some multimodal ones that use audio and video or audio and video and text. Also, our system is competitive with the state-of-the-art under similar evaluation settings. We conclude with the main takeaways. We've shown that sound separation can be seen as a valid augmentation to generate views for contrastive learning, and that learning to associate sound mixtures with their constituent separated channels elicits semantic structure in the learned representation. We've also demonstrated that sound separation can be successfully combined with other commonly used augmentations. We discovered that the transformations provided by different checkpoints of the same separation model as learning progresses are valid forms of augmentation for generating positives, and that sometimes can be complementary. In addition, we show the benefit of jointly training the proxy tasks of similarity maximization and coincidence prediction. And that's all. Thanks for listening, and please check our paper for more details.